This is a lesson introducing polynomial functions. Before we talk about polynomial functions, I think it's useful to talk about what is a polynomial. Most of you have an inherent idea. You've seen them lots of times. But let's look at a general form of all polynomials, specifically in one variable. They look like this. Now, some of you may think this looks like a giant jumble of letters, but let's break it into pieces known as terms. So now that we see this as terms, hopefully you can see that these terms have two parts. The first part is the variable. A polynomial in one variable is an expression where all the variables in every term are the same. In this case, it's x. The second thing that we want to look at are the coefficients. All the coefficients in a polynomial in one variable are complex, which means they're real numbers, which is pretty much every number you can think of. 1/2, the square root of 7, maybe -3, or imaginary. So think I, 4i, -2i, those types of numbers. The other condition for a polynomial in one variable is that the leading coefficient, that's the number that multiplies by the term with the highest exponent, is non-zero. That is this guy. So here's the general form for polynomials in one variable. It's probably more helpful to look at something more specific. This is a polynomial function. Notice that we have the same parts that we had on the last slide. So we have terms. We have 12x to the 5th as one term. We have 9x to the 4th as another term. We have -2x. And lastly, we have 1. What do we see in these terms? We see that every term has the same variable x. We also see that the term with the highest exponent has a coefficient other than 0, so we know that this is a polynomial function. When you look at polynomial functions, there are two very important ideas that you need to understand. The first one is the degree of the polynomial. The degree of the polynomial is the highest exponent in the polynomial. So of all these terms, and there are 4 here, of all the terms that I have, this term right here, 5, is the highest exponent. So the degree of this polynomial is 5. The degree of a polynomial is a really important idea, and you'll see as we move through this lesson that it's the degree of the polynomial that helps us to know how many solutions we have. And so it's critical that we have this skill of identifying the degree of a polynomial. The second thing that's important to look at when working with polynomial functions is the leading coefficient. Once you've identified the degree, if you look in the same term, the leading coefficient is going to be the coefficient, or the number, that multiplies by the variable to the highest power. The leading coefficient in this case is 12. So I'm going to write, and for short of leading coefficient, I'll just put LC. The leading coefficient here is 12. And you'll find in subsequent chapters an important idea when solving polynomial functions is finding the leading coefficient. That leading coefficient is going to help us find solutions later. So it's important to be able to identify the degree and identify the leading coefficient. Another really important idea for polynomial functions, of course, is solving them. So what does it mean to solve a polynomial function? It literally means to find the values of x that make the function equal to 0. We call these zeros. I think they're very aptly named. So let's say, for example, we're asked, what are the zeros of this function? That's the same thing as finding out what values of x make x squared minus 4x plus 3 equal to 0. I hope this expression looks familiar to you, because every time you've ever solved polynomial functions, you've solved them by setting them equal to 0. So zeros are another way of saying solve for x. There are a couple other vocabulary words that mean the same thing, and it's worth looking at these different vocabulary words. So we've just introduced the idea of zeros, the zeros of a function. And we just said that the zeros of a function are the same thing as the solutions. So I'm going to write the word solutions up here. These are all solutions. So what are the zeros of a function? The zeros of a function are the values of x when y is 0. Another word that you're going to see is roots. The roots of a function. The roots are the same thing as the zeros. And lastly, because we define zeros as the value of x when y is 0, we have this graphic representation. When x meets where y is 0, that's these guys right here. We call those x-intercepts. So this is the graphic interpretation of find x when y is 0. So these three things are equivalent to each other: zeros, roots, and x-intercepts. And all of these ideas basically lead us back to find the solutions. So when you see these four words, know that you can use them interchangeably. So a quick word about imaginary numbers. And we have to talk about imaginary numbers because sometimes the roots or zeros of our polynomial functions are imaginary. So I hope you remember that imaginary numbers are I, and they're defined as the square root of -1. And I'm actually going to talk really briefly about what happens when you square I, because a lot of times when we work with the zeros of polynomial functions, we end up multiplying imaginary numbers together and we get I squared. So I squared is going to be I, which is the square root of -1, squared. And when you square a radical, they cancel each other out and you get -1. So I squared is equal to -1. If you don't commit this idea to memory, that's okay. Hopefully you can work it out the way that I just did by squaring the square root of -1. Complex numbers are real numbers combined with imaginary numbers. So when I take a real number, like 3, and I add it or subtract it to an imaginary number, like 4i, if I consider these two numbers together in a binomial, then this is a complex number. And we have to talk about complex numbers because, again, our roots or our zeros are often complex numbers. So one of the most important ideas in this chapter, and this leads us to all of our work with solving polynomial functions, is the fundamental theorem of algebra. And most notably, one of its corollaries, and we'll get to that in just a minute. The fundamental theorem of algebra says that every polynomial function with a degree greater than 0 has at least one root in the set of complex numbers. I think sometimes when you read theorems like this, it's hard to really know what they're saying. So if we rewrite this a little bit, just look at what is it really telling us, what kind of, just get at the essence of this theorem, it's a really powerful idea. Basically, it's saying that every polynomial equation has at least one 0. Remember, zeros are the same as solutions. So this theorem is telling us that every polynomial equation has at least one solution. And secondary to that is that that solution could be real, imaginary, or complex. If we do a little bit of deductive thought, that leads us to the corollary for this theorem, and that is that polynomials of degree n have exactly n complex roots. This is the most powerful idea in this chapter because this basically leads us to finding all of the solutions. Remember, roots are solutions. All of the solutions. So polynomials of degree n have exactly n complex roots. So if I have polynomial of degree 5, it has 5 complex roots. And let's see why that is. So here's something of degree 1. Looking at the first graph, and you'll notice that it passes through the x-axis one time. Degree 2 passes through twice. Degree 3 passes through 3 times. Degree 4 4 times. Hopefully you're seeing a pattern here. Degree 5 passes through 5 times. Now, is this always the case? Does every degree 5 polynomial pass through the x-intercept, have 5 x-intercepts or pass through the x-axis 5 times? Certainly not. In some cases, let's look at this guy. Here's a degree 3 polynomial. It only passes through the x-axis 1 time, so it has 1 x-intercept. But the fundamental theorem of algebra tells us that I have to have 3 solutions because I have degree 3. And therefore, I know that the other 2 solutions are imaginary. So look, I have a total of 3 solutions. One of them's real because it's an x-intercept, and the other 2 must be imaginary. Let's look over here at this last one. Here's a degree 4 polynomial that doesn't pass through the x-axis at all. And that means that because it's degree 4, all 4 of my solutions, or all 4 of my roots, are going to be imaginary. Remember, the degree of the polynomial dictates the number of solutions. So then we have this other idea that all of our polynomial functions can be rewritten as a product of factors. Okay, a product of factors. And those factors are the variable x minus the roots. So how many factors I have depends on how many roots I have. So my factors in this case would be x minus the root. And in this case, my roots are r's. So this is kind of what it looks like generally. If I apply this more specifically, I get to use it on a problem like this. Write a polynomial with roots 5, negative 1/2, and 3. So this is like r1, and this is r2, and this is r3. So using the theorem that we just looked at, which says that I can write my polynomial as a product of factors, I can plug in the roots. 5, 3, and negative 1/2. Now all I have to do is multiply these guys together. So if I multiply x minus 5 times x minus 3, I get x squared minus 8x plus 15. Now I get that by multiplying these two guys together. Okay. Now over here I have x plus 1/2, which I got from doing x minus negative 1/2. And I've rewritten this as 2x plus 1 so that I don't have any fractions. And the way I do that is I basically am multiplying both sides of my equation by 2. It doesn't change the value of my equation because, as you can see, on this side of the equation it was always equal to 0. So if I multiply both sides by 2, this 2 multiplies in and gives me 2x plus 1. And the function stays equal to 0. So I haven't changed the value of anything. If I want to drop those fractions, I can. I like dropping those fractions because ultimately I'm going to have to multiply these two guys together. And it's a little bit easier to multiply these two polynomials together when I don't have any fractions. So we multiply them together, and this is my polynomial. So let's take a look at one that has roots that are imaginary or complex. Write a polynomial with roots 2, 4i, and negative 4i. So again, this is r1, this is r2, and this is r3. So I use my basic formula where the polynomial is the product of x minus the roots. I plug in the roots that they gave me, and I have to multiply this out. Now, x minus 4i times x plus 4i, what does that look like? I'm going to FOIL this out, so hopefully you remember how to FOIL, right? Firsts, outsides, insides, lasts. And when I do, I get x squared plus 4i minus 16i squared. I introduced the idea that I squared is negative 1. Remember, we looked at that earlier. And I get x squared plus 16. So I rewrite this as x squared plus 16. Then all I have left to do is multiply it by x minus 2, and I find my polynomial. And that's it.